Hello student, now we are going to discuss tubular transport. So how the different parts of nephron is handling different substances like for example sodium, glucose, etc. That will be discussed in this topic. Now to understand this, first I will give you a general overview. So in that overview, I am drawing a schematic diagram of a nephron. So this is Bowman's capsule along with this glomerular capillary, and then this is the proximal convoluted tubules and proximal straight tubules, followed by this is the loop of Henle, right? Descending and ascending part, and then the distal tubules, which is draining at the level of collecting duct. We all know this schematic diagram. Now we are going to understand that when the urine or the filtrate, glomerular filtrate, is passing through the different parts of nephron, how the tonicity or osmolality of the luminal content is changing with respect to plasma osmolality, right? So at the level of filtration, okay, the glomerular filtrate is always isotonic with that of the plasma. Means if you measure the osmolality of this glomerular filtrate, that will be same with that of the plasma. At the level of proximal tubule, remember, at the level of proximal tubule, the absorptions of solute is proportionate to the absorption of water. So whatever solute is absorbed at the level of proximal tubule, proportionate water reabsorption is also going on at the level of proximal tubule. So what will happen? If you take out solute as well as proportionate water, the tonicity is not going to change. So proximal tubule means the tonicity of the urine will remain isotonic, same with that of the plasma. Now when this isotonic urine is going to pass through this descending limb of loop of Henle, you have to remember about some point about this segment of special point. What is that special point? Special point is that this descending thin segment of loop of Henle is impermeable to any kind of solute. So only absorption that is possible in this segment is water. So I am writing here only water reabsorption is possible here, but no solute reabsorption is possible. Right, descending thin segment. So from a hypotonic solution, if you take out more and more water, okay, from isotonic solution, if you take out more and more water, what is going to happen? That isotonic will be concentrated more and more. So whenever the solution is passing through this descending thin segment of loop of Henle, it will get more and more concentrated, and finally when it will reach at the level of tip of loop of Henle, the tonicity will be hypertonic in nature. So the urine will be hypertonic in nature at the level of tip of loop of Henle. Okay. Now, when this hypertonic solution or the hypertonic urine is going to pass through this ascending limb of loop of Henle, mainly the TAL, that is the thick ascending limb of loop of Henle, this segment is opposite to the descending thin segment of the loop of Henle. What is the meaning of that? Meaning this segment is going to absorb only and only solute reabsorption is going to happen here, but no water reabsorption is possible in this segment, right? So TAL, that is the thick ascending limb of loop of Henle, is reabsorbing more and more solute from a hypertonic urine. So if you take out more and more solute without water, the hypertonic urine will gradually decrease in its tonicity. So what will happen? It will become isotonic, and followed by it will become hypotonic in nature, right? So that's why we say that if you look at the tonicity at the upper part of the TAL, it will be again converted into isotonic, followed by at the level of DCT, it will be converted into hypotonic. So when the solution or when the urine is passing through this distal tubule, okay, when the urine is passing through this distal tubule, the tonicity will be hypotonic. The urine tonicity will be hypotonic in nature, right? So At the level of density, further solute will be reabsorbed, so it will be more and more hypotonic when it is passing through the distal tubules. Now finally, this hypotonic urine will drain at the level of collecting duct. Now question is whether this hypotonic urine which is present in the collecting duct that will be excreted as it is, or it will be further concentrated at the level of collecting duct. This decision will be done by presence or absence of an important hormone, and that is nothing but ADH. So if the ADH hormone is present in blood, so the ADH is going to reabsorb huge amount of water at the level of collecting duct. Remember, ADH has only action at the level of collecting duct, right? So I will discuss that detailed version of water reabsorption, but for the time being, if the ADH is present, it is reabsorbing water from the collecting duct. So more and more water you reabsorb from this hypotonic urine at the level of collecting duct, what will happen? Finally, the urine will be hypertonic in nature. So if the ADH is present, the hypotonic urine which was present at the level of initial part of the collecting duct, that will be finally concentrated into hypertonic urine. This is in presence of ADH. Now if the ADH is absent at the level of collecting duct, the water reabsorption is almost nil if the ADH is absent, right? So if the ADH is present, obviously there will be huge amount of water reabsorption here, but if the ADH is absent, water is not going to be reabsorbed. So what will happen? This hypotonic urine which was there at the beginning part of the collecting duct, that will be converted into a little more hypotonic because this collecting duct is going to reabsorb certain solute like sodium. So in absence of ADH, the final tonicity of the urine will be hypotonic, more hypotonic than that of the distal tubule also when the ADH is absent. Getting my point? So it is the ADH hormone which is determining whether your final urine will be hypotonic or hypertonic or isotonic in nature. Now this concept, okay, general overview of different part of the nephron, okay, we have to understand with the help of a graph, because sometimes exam question can be given based on some graphical representation. So let me draw a graph first. Okay, so I am drawing this x-axis and y-axis of the graph. Okay, so x-axis is nothing but it is the length of different parts of nephron, right? So try to correlate this graph which I am drawing here with that of the above nephron picture. So in this nephron picture, from this up to this level, okay, where I'm marking this is the length of the proximal convoluted tubules. If I try to corroborate this with my graph, so I can understand that this length of nephron is nothing but proximal convoluted tubules or proximal tubule. Okay, then from here up to this level, this is the loop of Henle. So in my graph, this is nothing but the length of loop of Henle, right? And after that, you can easily identify that this is the portion which is nothing but the density. So in the x-axis, I am marking from here up to this level. This is the length of DCT or distal tubule, and then the remaining part is collecting duct. I hope you are understanding what we are going to plot, right? So x-axis is the different segment of the nephron. Okay, and what is y-axis? Y-axis will plot a very important parameter, that is TF upon P ratio. What is this TF upon P ratio? TF is the tubular fluid osmolality, okay, and P is the plasma osmolality. If I take a ratio between this, the tubular fluid, that is the urine osmolality, upon your plasma osmolality, that is TF upon P, tell me, if the urine is isotonic in nature, then what will happen to this ratio? Obviously, the ratio will be 1 because tubular fluid or urine osmolality is same to same with that of the plasma. So, I am pointing one point here on the curve. Suppose this is 1. This 1 indicate this is isotonic. So, now you draw the plot at the level of proximal table. So what will happen? This ratio will remain same to same throughout this proximal table. So the ratio is remaining same to same with that of 1 up to the level of this proximal table. Okay, so this is a straight line, almost straight line, that indicate throughout the proximal table the ratio is 1. Now what will happen when this urine is going to pass through this descending limb of loop of Henle? All of you know that more and more the urine is passing through the descending limb of loop of Henle, the urine will be more and more concentrated. So now I can understand that this TF upon P ratio is going to be increased, okay, and it will reach to a maximum value at the tip of loop of Henle. Okay, then when the urine is further going through this ascending limb of loop of Henle, this ascending limb is going to reabsorb only solute, no water. So that's why this ascending loop is known as diluting segment of the nephron. Means it is going to dilute the urine, hypertonic urine, which is present at the level of tip of loop of Henle. So what will happen to this TF upon P ratio? This ratio is going to be decreased. Okay, and it will be first converted into isotonic. Again look at, so this is parallel to 1, so this is isotonic at the end of loop of Henle, and then it will be converted into a hypotonic urine when it is passing through this DCT or distal convoluted tubules, right? So this way you can understand that what will happen to the TF upon P ratio in different segment of the nephron. But I told you that the final tonicity of the urine will be determined by ADH and the collecting duct functions, right? So if the ADH is present or absent, do you think this curve, this yellow color curve that I have made here, it is going to change? Answer is no, because ADH has no action in any of this part which we have plotted already, PCT, loop of Henle, DCT. Okay, the ADH has no action in this part. So suppose this yellow color curve, this is a curve which is in presence of ADH positive, and I am drawing another curve which is in absence of ADH. So the in absence of ADH curve will also remain parallel to this curve, or you can say this is a similar kind of curve will be seen if the ADH is absent. Up to which level? Up to the end of DCT. Now when this solution is, or the urine is passing through the collecting duct, what will happen? Tell me. In presence of ADH first, you first look at the yellow color curve. So ADH is present. Okay, now when this hypotonic urine from this DCT is reaching at the level of collecting duct, ADH will reabsorb more and more water, and the tonicity of the urine will further increase, and it will match almost the tonicity of the tip of loop of Henle. So this 2 point will be almost similar, it will match almost same to same, means urine is becoming hypertonic again, right? Hypertonic again. But now look at the green color curve. Green color curve means ADH is absent. So if the ADH is absent, this hypotonic urine which is present at the level of this DCT, hypotonic urine which is present at the level of DCT, that urine will be further hypotonic when it is passing through the level of the collecting duct, and you can see the graph here, the tonicity or the osmolality of the urine is decreasing further. So the hypotonic urine will be excreted in these cases when the ADH is absent. So what is the bottom line from here? Bottom line from here is that whether the ADH is there or not, up to the level of the DCT, okay, this hypotonic, isotonic, this will remain same to same whether it is ADH is present or absent. But if the ADH is present, then the urine tonicity will be further rise and it will be converted into hypertonic one. And if the ADH is absent, so urine will be more hypotonic at the level of end of collecting duct. So from this, if I ask you certain MCQ, what are the type of MCQ they will ask you here? So question is, in presence of ADH, presence of ADH, okay, maximum urine tonicity in which part of the nephron, and minimum urine tonicity in which part of the nephron? Now look at the curve. Okay, you look at the curve and try to answer. So in presence of ADH, so I am following this yellow color curve. So tonicity is rising, rising, rising. Then it is decreasing to a very low level at the level of DCT, further rising, 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 and it is matching with that of the tip of loop of Henle. So maximum tonicity is where? Where? Two answer can be possible at the end of collecting duct here or at the tip of loop of Henle. So that's why in presence of ADH, maximum urine tonicity, answer of this question will be end of collecting duct or tip of loop of Henle. Okay, but the best answer is the end of collecting duct, right? And minimum tonicity, so I have to find out where the urine is becoming hypotonic, right? So in presence of ADH, I can find out only it is the part of the DCT where the urine is becoming hypotonic. The TF upon P ratio is going below 1, right? So that's why the minimum tonicity of the urine will be present in which segment of the nephron? That is the DCT, distal convoluted tubules. Now looking at this, could you answer what will happen if the MCQ is asked like this, that in absence of ADH, when ADH is not there, right? In this condition, maximum urine tonicity will be in which part of the nephron and minimum urine tonicity will be in which part of the nephron. In absence of ADH, right? ADH is not there, maximum urine tonicity. So if you look at this green color curve, you are finding out that only one portion is reaching to a very peak. That is nothing but tip of loop of Henle, and after that the curve is going down, down, down only, right? So what will be the answer in absence of ADH? In absence of ADH, only answer possible is tip of loop of Henle. Tip of loop of Henle. But if I ask you minimum urine tonicity, now minimum point, I told you here that after this loop of Henle, tip of loop of Henle, the curve is going down, 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 and minimum tonicity is reaching here. That is nothing but end of collecting duct. So that's why the minimum urine tonicity, the answer of this question will be end of collecting duct. Getting my point? So this way MCQ become difficult if you don't understand the concept. So please try to remember that although we know this concept that PCT means isotonic, right? Okay, tip of loop of Henle means hypertonic, okay, and then isotonic at the upper part of the TL and hypotonic at the level of collecting duct, and final tonicity will be determined by collecting duct. We know this part. Okay, but you have to remember that apart from this TF upon P concept is also important. TF upon P, 1 means that is isotonic, less than 1 means hypotonic, more than 1 means hypertonic. So this way you have to answer different question. So this is the first part of general overview. Now the second part, okay, second concept for this tubular transport that you require is glomerulo-tubular balance. Glomerulo-tubular balance. Okay, so it is a balance between glomerulus and tubules. Okay, previously we have seen another concept that is known as tubulo-glomerular feedback. I hope you remember that. Tubulo-glomerular feedback means that macula densa, that is a part of tubules, is giving feedback to the level of glomerulus. That is the tubulo-glomerular feedback, and here it is glomerulo-tubular balance. So there is a balance between glomerular filtration and tubular reabsorption. That balance is known as glomerulo-tubular balance. To understand that, look at my diagram. Okay, first, okay, so I am drawing this capillary. The same diagram, the similar diagram you have seen multiple times, right? Glomerular capillary, and then surrounding this is Bowman's capsule, okay, where filtration is occurring. The concept is very simple, that whenever there is increase in filtration, reabsorption at the level of proximal tubule will increase proportionally. Balance. More filtration means more reabsorption. That is the simple thing, which is the meaning of glomerulotubular balance. So what I'm saying, suppose the blood is reaching here through the afferent arteriole. The blood which is reaching at the level of glomerular capillary, okay, that contain 100 molecule of sodium, right? 100 molecule of sodium, okay, and that 100 molecule of sodium is getting filtrated. Just for example, suppose 100 molecule of sodium is getting filtrated. Within this 100 molecule of sodium, at the level of proximal tubule, how much is going to be reabsorbed? The percentage is 65 to 70 percentage. So suppose within this 100 molecule of sodium, okay, the proximal tubule is going to reabsorb 70 molecule of sodium. So that is the reabsorption at the level of proximal tubule. Now, due to any reason, if this filtration is increased, suppose now the filtration is 200 molecule of sodium is getting filtrated, what will happen? Proportionate reabsorption from this proximal tubule will also increase. That means now the proximal tubule is going to reabsorb 140 molecule of sodium, means doubling of the filtration is doubling the reabsorption. That means I can understand that this glomerulotubular balance is keeping the fraction or the percentage reabsorption constant. What is the meaning of that? Previously it was reabsorbing from 100 to 70. How much percentage? 70 percentage. Now within this 200 it is reabsorbing 140. How much percentage? 70 percentage. Means from this glomerulus up to the level of this proximal tubule, there is a balance. This balance is maintained in such a way that the percentage reabsorption at the level of proximal tubule remain constant. Getting my point? This concept is known as glomerulotubular balance, right? So balance is keeping the fraction of reabsorption or the percentage of reabsorption at the level of PCT constant. That is simple concept. Now question is how the balance is maintained. What is the mechanism of this balance? Okay. Now you tell me, whenever any kind of reabsorption is occurring at the level of proximal tubule or any part of the tubule, suppose sodium is reabsorbed or chloride is reabsorbed, what is the fate of this sodium or the chloride which is being reabsorbed from the lumen of this nephron at the level of the interstitial space? The reabsorption has been done. What is the fate of this sodium from the interstitial space where it is going to enter? Obviously, it is going to enter at the level of capillaries. Which capillaries? The capillaries which are present here. That is nothing but the peritubular capillary. That capillary, that is nothing but peritubular capillary. So this is peritubular capillaries, right? Okay. Now always remember, whenever you are reabsorbing more from the proximal tubule or any part of the tubule, the peritubular capillary has to reabsorb them proportionally, right? Otherwise, the concentration of the sodium in the interstitial space will be more and that will oppose the further reabsorption. That way, ultimate reabsorption means the peritubular capillary is reabsorbing. Although the step is that from the lumen of this nephron, it is entering in the interstitial space. From that interstitial space, it is entering into the level of the peritubular capillary. But ultimately, it is the peritubular capillary which is going to be reabsorbed. Now, peritubular capillary reabsorption means the reabsorption will be based on two forces mainly. We have seen the Stirling forces. So, Stirling forces means if the peritubular capillary hydrostatic pressure is low, okay, then it will be helpful for reabsorption. Because whenever the hydrostatic pressure is low inside the capillary, what it will do? It will reabsorb water. And along with water, the solute, along with solvent, the solute is going to reach in the peritubular capillary. Similarly, if I ask you what you require about this, what you require, the oncotic pressure at the level of peritubular capillary should be low or high. If you want to reabsorb more in the peritubular capillary, it has to be high, because oncotic force is a kind of retaining force. It will try to retain more water inside the peritubular capillary, so it will drag more water. Along with water, the solute will also reabsorb. So basically, these two forces at the level of peritubular capillary are helpful for reabsorption. Either you increase the oncotic pressure or you decrease the peritubular capillary hydrostatic pressure, right? Now, in respect to this glomerulotubular balance, whenever filtration is increased, means more water is filtered at the level of glomerulus. That is the meaning of increase in glomerular filtration, right? So whenever there is increase in filtration, more water is entering from the glomerular capillary to Bowman's capsule. What will happen to the concentration of protein concentration at the level of this efferent arteriole, followed by protein concentration at the level of peritubular capillary. So I'm asking you that whenever there is increased filtration at the level of glomerular capillary, what will happen to the concentration of protein? Because protein is not going to filtrate. Protein concentration increases at the level of efferent arterioles. Whenever the protein concentration is high at the level of efferent arteriole, that blood is ultimately going to flow through the peritubular capillary. So what will happen? The oncotic pressure of peritubular capillary, oncotic pressure of peritubular capillary is going to rise. An increase in oncotic pressure of peritubular capillary will leads to increase absorption or reabsorption at the level of capillaries blood, So that's why I told you that whenever there is more filtration, more reabsorption is only possible because the oncotic pressure at the level of peritubular capillary is becoming higher. So now if I ask you, what is the main reason or mechanism for this glomerulotubular balance? More filtration means more increase in oncotic pressure of the peritubular capillary, and that is reabsorbing more amount of solute as well as water. This is known as glomerulotubular balance. I hope you get it. Okay. Now, after these two concepts, okay, now we are going to understand absorption of different substances individually. Okay, means sodium, potassium, glucose, individual reabsorption of different substances. The first substances that we are going to discuss is sodium reabsorption. Okay, sodium reabsorption in different parts of nephron. Why we are starting with sodium? Because many reabsorption are coupled with sodium reabsorption. Okay, sodium along with chloride, sodium along with phosphate, sodium along with amino acid. So many reabsorptions are coupled with sodium reabsorption. So if you understand sodium reabsorption, many things you will understand in a clear fashion. So that's why we are starting with sodium reabsorption in different part of nephron. Now before starting, if I ask you, is there any secretion of sodium in any part of the nephron? Answer is no. Only filtration, freely filterable substances, and then there will be reabsorption. How much percentage of total filtrate is going to be reabsorbed? So suppose the filtration amount of sodium is 100%. From this 100%, how much is going to be reabsorbed? Remember, the proximal table, okay, the proximal table is going to be reabsorbed 65 to 70% of the total filtrate sodium, right? Then TAL, thick ascending limb of loop of Henle, is going to reabsorb another 25 to 30%, right? So 60 plus 30, almost 90% is reabsorbed. Now DCT, okay, is going to reabsorb only 5 to 7%, okay, and collecting duct is going to reabsorb 2 to 3%. Oh my god, almost 100% you have written, sir. Yes, the total reabsorption of sodium is 99.6%. So if the filtration amount of sodium is 100%, within that 100% sodium, 99.6% of sodium is going to be reabsorbed. Now if you note down here, every part is reabsorbing sodium except sodium reabsorption is not possible at the level of DTS, that is the descending thin segment of the loop of Henle, which is not only for sodium, this is impermeable for any solute. So that's why DTS, descending thin segment of the loop of Henle, is not going to reabsorb sodium. All other part is reabsorbing sodium. Now, in every part of the nephron, whether it is proximal tubule, TL, distal tubule, or collecting duct, sodium reabsorption is mainly active, although passive is also there. What I told, active plus passive both are there, but active is the main component in any part, except one part of nephron is there where only passive reabsorption of sodium is possible. Only passive sodium reabsorption, only passive sodium reabsorption is there at the level of ATS, ascending thin segment of the loop of Henle, ascending thin segment of the loop of Henle, which is mainly seen in juxtaglomerular JM, juxtamedullary type of nephron, right? The cortical nephron, this ATS, ascending thin segment, is very small, or it can absent, is written in many books. So only passive reabsorption of sodium is possible in which segment of the nephron? Ascending thin segment of the nephron. In rest of the part, the sodium reabsorption is mainly active, although passive is also possible, and DTS, it does not take part in sodium reabsorption. Not only sodium, for any solute this is true. Now we have to understand the mechanism behind sodium reabsorption in each of this part, the mechanism behind sodium reabsorption. And whenever we will be discussing this mechanism, we will understand that the sodium reabsorption is coupled with many other reabsorption, right? So we are starting with the proximal tubular mechanism. Proximal tubules, okay? Proximal tubule, how it is reabsorbing sodium. 65%, 70% of sodium is going to be reabsorbed here. So first I am drawing a diagram. In that diagram, I'll draw the epithelium cell of proximal tubule. Okay, so this is the single epithelium cell from the level of proximal tubule, right? And I'm drawing another cell. So these two cells are located near to each other. Okay, so this will also this is also a big cell. Okay, so two epithelium cells located with one another, and in between these two epithelium cell, the apical portion of these two epithelium cell, they're connected with the help of tight junction. I hope you remember the first class of renal physiology, right? So this direction, this is the luminal, this is the lumen of the nephron, and this is the basolateral membrane of the epithelium cell. I hope you know that. So this is the lumen. So whatever filtration is occurring from glomerulus, that filtration is reaching at the level of lumen, and that filtration contain huge amount of sodium and other solutes. So I have to reabsorb. Reabsorption means first it will enter from this lumen to cell, and from that cell to the peritubular capillary blood. So peritubular capillary blood is located here. So this is the capillary, peritubular capillary, right? I hope you got the diagram. This kind of diagram we are going to draw again and again, so that's why I am explaining it a little bit more, right? So sodium reabsorption occurs through various transporter protein or carrier protein. So number one carrier protein that I am writing here, all of you know this, it will absorb sodium along with glucose. It is reabsorbing sodium along with glucose. So what is the name of this transporter? SGLT, sodium glucose linked transporter. I hope all of you know. So if I ask you, this is a which kind of transport? Secondary active transport. So all this transporter, I will draw three groups of transporter. All of them are secondary active transporter, right? Then second, this transporter is reabsorbing sodium along with various other substances, like for example, sodium along with amino acid. So sodium amino acid co-transporter, or sodium along with phosphate. Okay, so sodium phosphate co-transporter, sodium along with citric acid, so sodium citric acid co-transporter. So I'm writing here that this is nothing but various other co-transporter are also helping in sodium reabsorption. And the third group of transporter that I'm drawing here, this transporter is very special. Why special? Because whenever it is reabsorbing sodium from lumen to the epithelium cell, it is going to secrete one molecule of H plus ion into the lumen. Means it is an antiporter, it's not a co-transporter, it is an antiporter which is absorbing sodium in exchange with H plus ion. That's why the name of this transporter is NHE, sodium hydrogen exchanger. So the sodium hydrogen exchanger is secreting acid at the level of proximal convoluted tubules, but that acid is not going to acidify your urine. This concept you will understand in the next chapter, acidification of the urine, that chapter. Okay, but for the time being, you remember that three major group of transporter is reabsorbing sodium at the level of proximal tubule: sodium glucose co-transporter, that is the SGLT, sodium along with other molecule like amino acid, citrate, phosphate. So there are various other groups of co-transporter there, and sodium in exchange with hydrogen, that is sodium hydrogen exchanger. Now obvious question is, among these three groups of transporter, all of them are secondary active transporter, which one is going to reabsorb maximum percentage or maximum amount of sodium? Answer is not SGLT. Please remember, SGLT is responsible for only 5% of the total sodium reabsorption from proximal tubule. Another 45% sodium is reabsorbed by various co-transporter, and maximum sodium reabsorption from the proximal tubule is done by NHE. Very important concept. SGLT is the transporter which is responsible for glucose absorption. 100% glucose reabsorption is done by SGLT, but that does not mean SGLT is responsible for 100% glucose reabsorption. It is responsible for only 5% of sodium reabsorption from the proximal tubule, right? So now, I hope you are going to remember this, that NHE is the transporter which is absorbing maximum sodium from the lumen to cells. Now, if you look at the basolateral membrane, you have to throw the sodium from this cell interior up to the level of this capillary blood. So you require another transporter which will transport sodium from the cell at the level of capillary blood. Okay, so this transporter is throwing sodium against the concentration gradient from the cell to the blood, and it will do this in exchange of potassium. So now you can understand what is this transporter. This transporter is the universal transporter, that is nothing but sodium potassium ATPase pump, right? So please remember, from the basolateral side, maximum sodium is reabsorbed by sodium potassium ATPase pump. That is the dominant transporter. Whatever sodium is entering at the level of cell cytoplasm, all that sodium will be thrown out of the cell into the capillary blood by the sodium potassium ATPase pump, which is located on the basolateral membrane. So that is the maximum absorbing transport pump at the basolateral aspect. Along with this sodium potassium ATPase pump, sodium bicarbonate co-transporter is also there. So sodium bicarbonate co-transporter, which is known as NBC, sodium bicarbonate co-transporter, is also there, which helps in sodium reabsorption in the basolateral membrane. So please be careful that whether the question is asking about the luminal membrane sodium reabsorption or basolateral membrane sodium reabsorption. Basolateral means maximum is sodium potassium ATPase pump, but luminal membrane means maximum sodium is reabsorbed by sodium hydrogen exchanger. Now, apart from this, I have to remember that this sodium hydrogen exchanger, that this transporter is stimulated by hormone angiotensin 2. So if you stimulate this NH transporter by angiotensin 2, what will happen? It will reabsorb more and more sodium from the lumen to the cell, means blood sodium level will increase. That's why I told you in one of the session that angiotensin not only for vasoconstriction, it is also for sodium reabsorption from the nephron lumen, and that is done by stimulating the NHE transporter. So now if I ask you all these transporter protein that I have discussed here, which is reabsorbing sodium, what kind of transporter they are? Okay, apart from this sodium potassium ATPase pump, all others are secondary active transporter. That's why I told you that sodium reabsorption at the level of proximal table is which kind of reabsorption? Active reabsorption of sodium. But is there any passive reabsorption of sodium is possible? Answer is yes, yes, yes. Why? This tight junction which is present at the level of proximal convoluted tables or proximal tables, that is leaky in nature. Leaky in nature means some of the sodium can easily pass through this paracellular pathway, which is not going through the cell membrane. So the paracellular type of transport is a kind of passive transport. So at the level of proximal table, not only active transport, passive transport of sodium is also possible. Passive reabsorption of sodium is also possible, but active is a little more than that of the passive reabsorption. Got it? So this is all about the proximal tubular sodium reabsorption, right? Now, proximal table, if you look at more closely, I told you it has two parts, proximal convoluted table. So the thing that we have discussed here, this is mainly at the level of proximal convoluted tables. Why are you saying so, sir? Because if you look at the sodium reabsorption at the level of proximal straight tubules, which is the second portion of the proximal table, okay, here sodium reabsorptions occurs. Sodium reabsorptions occur along with chloride reabsorption. What is the importance of this? Remember, in the PCT, the proximal convoluted table, there are SGLT, there are co-transporter, there are NEG, which is reabsorbing sodium along with various other substances like amino acid, glucose, etc., etc. And on the basolateral membrane, it is reabsorbing bicarbonate along with sodium, right? We have not discussed about chloride in the proximal convoluted tables. Proximal convoluted tables is a little bit impermeable for chloride reabsorption. So generally sodium reabsorption occurs along with chloride, we know that, but in the proximal convoluted tables per se, sodium is specially reabsorbed with other kind of substances like for example glucose and all, and sodium is also reabsorbed along with the bicarbonate, leaving chloride in the proximal convoluted tubular lumen. So when the chloride is going to be reabsorbed, chloride is going to be reabsorbed in the later part of the proximal tubule, that is nothing but proximal straight tubule. So that's why if you look at the chloride concentration throughout the proximal tubule, it will little bit increase from this beginning part of the proximal tubule towards the ending part. Whenever you are moving towards the proximal straight tubule, chloride concentration will increase a little bit, and then the chloride absorption will occur at the level of later part of the proximal tubule along with sodium, right? So the proximal straight tubule means sodium reabsorption occurs along with chloride. Then the next part of the nephron is nothing but, after proximal straight tubule, the next part is nothing but descending thin segment of the loop of Henle. Is there any sodium reabsorption here? Answer is no. So no sodium reabsorption, no sodium reabsorption at this descending thin segment, right? Then after descending thin segment, there is ATS, that is the ascending thin segment of the loop of Henle. This part of the nephron is specially present at the level of juxtamedullary type of nephron, and I told you already that this is the part of nephron where sodium absorption is only and only passive. So passive reabsorption of sodium along with chloride. Passive reabsorption means how this reabsorption is going to happen in the paracellular pathway. Paracellular pathway, not through the cell membrane, not through the transcellular route. It is going to happen through the paracellular pathway, right? Now, after the ATS, the next segment of the nephron is TAL, that is the thick ascending limb of loop of Henle, TL. So it is going to reabsorb a major portion of the sodium, major chunk of sodium, 25 to 30%, like that of the proximal tubule, right? So what is the mechanism of sodium reabsorption at the level of TAL, right? We are going to discuss this concept again with the help of a diagram. So this is the epithelium cell of the TAL. I'm going to draw another epithelium cell of the TAL. So this is another epithelium cell of TAL, thick ascending limb of loop of lamp. So in between these two cells, there will be tight junction at the apical most portion. So obviously, this is the luminal side of nephron. So whatever sodium is there at the level of lumen of the TL, that sodium is going to reabsorb by a transporter protein. All of you know this transporter protein. This transporter protein reabsorb not only sodium, so it reabsorb one molecule of sodium, okay, one molecule of potassium, and two molecule of chloride. Okay, electroneutral transport. Okay, one positive plus two negative, electroneutral kind of transport. So this transporter, which is reabsorbing one molecule of sodium, one molecule of potassium, two molecule of chloride, this is typically known as NKCC transporter, sodium potassium chloride channel, NKCC, sodium potassium 2 chloride channel, right? That is the NKCC transporter, which is reabsorbing sodium, potassium and 2 chloride. And all of you know this transporter. Why? Because this is the transporter which is blocked by furosemide diuretics, Lasix diuretics, right? So after reabsorption of this sodium, potassium and chloride, what is going to happen? The sodium has to be reabsorbed from this basolateral aspect also, that and then only the sodium is going to reach at the level of peritubular capillary. So who will do that? The same pump which is universally present in almost all cell, that is nothing but sodium potassium ATPase pump. So it will reabsorb sodium from the cell cytoplasm to the capillary blood. How the chloride will be reabsorbed? Okay, I'm coming to potassium a little later. Chloride will be reabsorbed by a separate channel. Okay, chloride will be reabsorbed into the peritubular capillary blood by a separate channel. This channel is known as CLC, that is a chloride channel, KB subtype. CLC, that is a chloride channel, KB type of subvariety, which is there on the basolateral aspect of the cell, and this channel is specially reabsorbing chloride from the lumen cell cytoplasm to the level of capillary blood. Okay, now this CLCKB, that is a chloride channel, basolateral chloride channel, is helped by a protein which is always associated with this channel, and that protein which is always present with this channel is known as BRTTIN. This is known as the Burtin protein. The Burtin protein is always present with this CLCKB channel, and it is helpful for the channel proper functions, right? So you have to remember this Burtin. Now what about potassium? Okay, potassium after reabsorptions, it is going to be diffused back into the lumen. It is going to diffuse back into the lumen. Okay, so it is again returning to the level of the lumen of the TAL with the help of a channel. This channel is known as ROMK channel, renal outer medullary potassium channel. Renal outer medullary potassium channel, that is ROMK channel, renal outer medullary. This channel was first time discovered in the outer segment of the medulla, that's why this is known as the renal outer medullary potassium channel. So the potassium is diffusing back into the lumen once again. So what is happening now? You look at the whole phenomena. So the NKCC channel, NKCC transporter, it is transporting, reabsorbing one molecule of sodium, one molecule of potassium, two molecule of chloride, absolute electroneutral. After that, it is giving back one molecule of potassium again into the lumen. So when it is reabsorbing this one molecule of sodium, one molecule of potassium, two molecule of chloride, the charge of the lumen is not going to alter because it is electroneutral reabsorption. So whatever was the charge in the lumen, that luminal charge will remain intact whenever you are absorbing one sodium, one potassium, two chloride. Now you are giving back one molecule of extra potassium which was there in the lumen, then you have reabsorbed, now you are returning back. So what will happen? Whenever you are returning back one molecule of potassium again back to lumen, you are giving one molecule of positive charge. So the lumen will become positively charged. This is known as lumen positive charge, right? So due to diffusion back of potassium into the lumen again, the lumen will be positively charged. Whenever lumen become positively charged, whatever positively charged ions which are present there in the lumen, like for example calcium, that is a positively charged molecule, it was also there in the lumen, it is also there in the urine. Magnesium, which is also a positively charged molecule, which is already there in the lumen, which is already there in the urine, this positively charged molecule will be pushed, okay, because there will be repulsion between this positive charge. So because of this repulsion of the lumen positive charge and this positively charged ion, this positively charged ion will be pushed through this, okay, paracellular pathway, through this tight junction, and it will be reabsorbed into your capillary blood. So if I ask you, this kind of calcium reabsorption and magnesium reabsorption, what kind of reabsorption they are, active or passive? Obviously, this reabsorption is occurring through paracellular pathway. So this is a kind of passive reabsorption of calcium and magnesium. Now please note down, by this process, okay, by this paracellular transport at the level of TL, magnesium reabsorption which is happening, that is the maximum percentage of magnesium reabsorption among any segment of the nephron. What I am saying, I am repeating. If I ask you, calcium reabsorption is maximum in which part of the nephron? PCT. Sodium reabsorption, PCT. Bicarbonate, PCT. Everything, maximum reabsorption occur at the level of PCT, except this magnesium, where maximum reabsorption of magnesium is occurring in which part of the nephron? TAL. By which process? By passive paracellular reabsorption. And what about calcium? By this way, calcium reabsorption at the level of TL is only 25%. So basically, calcium reabsorption, okay, they maximally occur at the level of PCT. PCT reabsorbs 65% of the calcium, right? And this TAL, it reabsorbs only 25% of the calcium. But if you look at the magnesium reabsorption at the level of PCT is only 10 to 15% of the total magnesium. And at the level of TAL, this is the maximum percentage, that is 70% of the total magnesium reabsorption occur at the level of TAL. That's why this can be an MCQ, that maximum reabsorption of magnesium occurs in which segment of the nephron? That is the TAL and passive process. Now you look at, okay, so now we know the various mechanism by which sodium reabsorption is occurring at the level of TAL, right? So very important is that this NKCC transporter. I told you already that this transporter is inhibited by your diuretics, that is furosemide. Okay, furosemide. So this diuretics, whenever it is inhibiting NKCC, obviously the sodium reabsorption is not going to happen from lumen of the nephron. So sodium is going to be excreted in the urine at a high volume, right? So sodium excretion means it is excrete more amount of water also. Okay, so potassium will also be excreted more in the urine. So hypokalemia is going to be developed by these diuretics in long-term standing therapy. Obviously you can understand, because sodium is going to lost in the urine, potassium is also going to lost in the urine, and chloride reabsorption will also be inhibited here at this. But look at, along with that, whenever you are inhibiting this NKCC transporter, okay, you are not absorbing sodium potassium 2 chloride. So this potassium returning back to the level of lumen, that is also not going to happen, because if you are not reabsorbing, then how can you return? So this returning back of potassium, diffusion back of potassium is also not going to happen if you give furosemide diuretics therapy. So if the potassium is not returning to the lumen, this positively charged lumen membrane is not going to develop. If the positively charge is not there on the luminal membrane, do you think this calcium and magnesium is going to be reabsorbed? Answer is no. And that's why whenever you are giving furosemide diuretics therapy on a long-standing basis, sodium loss will be there in the urine, potassium loss will be there in the urine. Along with that, calcium, magnesium loss will also be there at the level of urine, right? So that's why long-standing furosemide diuretics therapy, you have to be cautious. calcium level in your blood may be lower, because this 25% calcium reabsorption which is occurring at the level of TL, that will be inhibited. Get it? Okay, right. So now the second concept is that mutation of the NKCC is possible in a disease, and that disease, all of you know, that is nothing but Bartter syndrome, right? So I'm writing here, okay, Bartter syndrome has different subvariety, okay, BRTTL, Bartter's syndrome, right? So Bartter syndrome, in this condition, the main mutation is at the level of NKCC. But if you open medicine books like Harrison, they are classifying this Bartter syndrome into different subcategory, like type 1 Bartter syndrome, right? Here, the mutation occurs at the level of NKCC transporter, right? Bartter syndrome type 2, right? Mutation occurs at the level of ROMK channel. So all these channels which we have discussed here, so NKCC, okay, then this ROMK, they can also be mutated in Bartter syndrome. The third one, this chloride channel, and the fourth one is this Burden protein. So all of them can get mutated in Bartter syndrome. Type 1 means NKCC, type 2 means ROMK, right? Type 3 means, okay, so obviously the chloride channel, the basolateral chloride channel, that is CLC, KB variety of channel mutation, right? And type 4, sometimes it is said type 4, okay, so type 4 is mutation of this protein which is helping this CLCV channel, that is nothing but BARTTIN, Bartin protein, right? So this Bartin protein can also get mutated, okay, in case of certain type 4 Bartter syndrome. And this Bartin protein which is helping this basolateral chloride channel, the similar kind of chloride channel and this Bartin protein is also present at the level of internal ear, the stria vascularis of internal ear. This Bartin protein is also present there, because of which whenever one person is suffering from this type 4 Bartter syndrome, the Bartin protein is mutated, not only the person will suffer from problem at the level of renal system, but also the person will suffer from sensory neural deafness. Sensory neural deafness. That's why type 4 Bartter syndrome is associated with sensory neural deafness. Right? I hope you got it. So this is about NKCC mutation and Bartter syndrome. Now we look at, I told you that paracellular transport of this calcium and magnesium, where it is occurring through this tight junction. Tight junction. Do you remember the tight junction is formed by which protein? Yes, the tight junction is formed by a main protein which is known as CLAUDIN. There are different subvariety of this claudin protein or claudin gene. Okay, the claudin protein which is present at the level of this TAL tight junction is claudin 16, which code a protein. This is basically a gene. Claudin 16 is a gene. That gene is coding a protein. That protein is paracellin 1. That is coding a protein which is known as paracellin 1. If there is mutation of this claudin 16 gene or paracellin 1 protein, then also, okay, there will be loss of magnesium in the urine, because you will not be able to reabsorb this magnesium and calcium, and that disease is known as familial, okay, familial hypomagnesemia, familial hypomagnesemia, right, along with hypercalciuria, hypercalciuria. More calcium in the urine, more magnesium in the urine, blood magnesium level will be very lower, because this is the portion which is reabsorbing huge amount of magnesium. That's why the disease is known as familial hypomagnesemia along with hypercalciuria, right? So this is all about the sodium reabsorption at the level of TAL. What is the next part of the nephron? The next part is the DCT, right? So now we are going to discuss the sodium reabsorption at the level of DCT. Less amount of sodium reabsorption occur here, but important one. Okay, so again the same kind of diagram I am going to draw here. This is the epithelium cell of DCT, and another epithelium cell you can also draw near to this, and in between them there will be presence of tight junction will be present here. So this is the presence of tight junction. Okay, so luminal side, and this is the basolateral side. So from the luminal side, who is going to reabsorb sodium at the level of DCT? All of you know this transporter protein. So here the sodium reabsorption occur along with chloride only. One sodium, one chloride. Potassium is not here. So this transporter is known as NCC, sodium chloride channel. NCC, sodium chloride channel, is reabsorbing sodium. And from the basolateral aspect, the same transporter, the same pump is going to reabsorb sodium, that is sodium, potassium, ATPase pump, that is reabsorbing sodium from basolateral aspect. This is very simple. And this NCC transporter is inhibited by our diuretics. All of you know that diuretics, that is inhibited by our diuretics, which is nothing but thiazide, right? So that is inhibiting sodium reabsorption at the level of DCT. Now, apart from this sodium reabsorption at the level of DCT, this segment is very, very important because calcium reabsorption occurs at the level of DCT, and this is the only part of the nephron where calcium reabsorption is only active. What I am saying? Look at. Previously I told you calcium reabsorption occurs at the level of PCT, TL, huge percentage. If I ask you calcium reabsorption here is active or passive, it is mainly and mainly passive reabsorption of calcium, although active is there, but that active is very, very less. Okay, mainly and mainly calcium reabsorption at the level of PCT, TLs, passive. What about magnesium? It is also passive, and it is only passive. Active reabsorption is not possible here. Getting my point? Now we are reaching at a segment of nephron, that is the DCT, where calcium reabsorption is only active. Right? That's why you have to remember, because active reabsorption means that portion that he will be regulated by various hormones. Okay, so look at. So from the lumen of DCT, calcium will be reabsorbed by a channel. This channel is important. Okay, this channel is known as TRPV5 and TRPV type 6. What is this TRPV? If you have already read the CNS, then TRP, that is the transient receptor potential channel, we call it as a transient receptor potential channel, right? Potential channel. It has different subvariety. Here it is V, right? Vanilloid, TRPV. Which subvariety? TRPV5 and V6. This is a channel. This channel you will read detail in central nervous system. We will discuss about pain receptor, nociceptor discussion. That time the detailed version will be dealt with. But for the time being, remember the same TRPV is also there at the luminal membrane of DCT, which is helpful for reabsorption of calcium. Then the calcium will enter inside the cell. Okay, but if the calcium is becoming more and more inside the cell, so you are absorbing more and more calcium, intracellular calcium will go on rising. If the intracellular calcium is very high, this will prevent further reabsorption of calcium from this lumen. So always I have to keep intracellular calcium lower. Then and then only more calcium is going to reabsorb from lumen to cell. Okay, you have to keep intracellular calcium lower. How you can keep intracellular calcium lower? There is a binding protein for this calcium. Whenever free calcium is present in the lumen, whenever free calcium is present in the cell cytoplasm, that calcium will be taken up by this binding protein. It will bind with the calcium, and the free calcium will be decreased inside the cells. This binding protein, which is kind of buffer protein for calcium, which is buffering the calcium, it is not allowing the calcium concentration, free concentration, to rise inside the cell. This is known as cal binding protein, ClBindDin, cal binding, calcium binding protein. Now this calcium binding protein not only binds calcium and keep the calcium concentration lower, it will also bring the calcium from the luminal side of the membrane towards the basolateral side. Means it's a carrier protein of calcium also. Intracellular carrier. It is carrying the calcium from luminal membrane towards the basolateral membrane. So it's like a boat. With the help of this boat, calcium is transported from luminal membrane towards the basolateral membrane. Now at the level of basolateral membrane, there is a exchanger protein for calcium reabsorption, and this throw calcium out of the cell, so it is reabsorbing calcium in exchange with sodium. So obviously this is nothing but NCX, sodium calcium exchanger, right? So now you look at the whole process of calcium reabsorption from DCT, the active reabsorption of calcium. NCX is a secondary active transporter. Okay, that's why the calcium reabsorption is active. So from the lumen to cell, that is the TRPV5 and TRPV6, from the cell cytoplasm to blood, that is NCX, sodium calcium exchanger, right? Please note down. So now whenever you want to reabsorb more calcium, I told you we have to keep the free calcium concentration low inside the cell. Not only that, you have to keep this NCX fully functional. What do you mean by fully functional? Look at the mechanism of this NCX. NCX is reabsorbing sodium from the cell and it is reabsorbing calcium from the cell, and in exchange sodium is entering inside the cell. So more you absorb calcium from the cell, the sodium concentration will rise inside the cell. But if the sodium concentration inside the cell is rising more and more, further sodium will not be able to enter inside the cell. So not only calcium, I have to keep sodium concentration low inside the cell. If I keep sodium concentration low, then this NCX transporter will be functional and it will throw more and more calcium out of the cell. That will lead to absorption of further calcium. So by any mechanism, if you keep low sodium concentration in DCT cell, then calcium reabsorption will increase. Now you look at the mechanism of this thiazide. Thiazide is inhibiting the NCC transporter. So the sodium reabsorption will be inhibited. If the sodium reabsorption from the lumen is inhibited by NCC, what will happen to the sodium concentration in the cell? Low. Which reabsorption will increase? Calcium. That's why we say that thiazide diuretics therapy increases calcium reabsorption from the level of DCT, right? And that's why all of you know that because of this reason, thiazide is the drug of choice for one disease, that is idiopathic hypercalciuria. So if the calcium level is very high in your urine, calcium is excreted very high in your urine, you do not know what is the cause of that, you give thiazide diuretics, it will reabsorb more calcium from the urine, and that will prevent the stone formation at the level of urine, calcium stone formation at the level of urine. So that way this thiazide diuretics is preventing sodium reabsorption, but whenever you prevent sodium reabsorption, sodium concentration will be low in the cell, and that will lead to reabsorption of the more calcium from the lumen. This is the mechanism which you have to remember. Not only that, this DCT, I told you that DCT is the segment where calcium reabsorption is active, only active. In other places, active reabsorption of calcium is very minute percentage, but here it is the only active reabsorption of calcium. That's why this is the segment where different hormones also act. What is that hormone? PTH, parathyroid hormone, stimulate this TRPV5 and 6. So if you stimulate TRPV5 and 6, what will happen to your calcium reabsorption? Increases, and that is a mechanism which you know. So that's why we say parathyroid increases calcium reabsorption. What is the site of action of this mechanism? That is the DCT. How it is increasing calcium reabsorption? By stimulating TRP5, V5 and V6, right? Vitamin D3, it also increases calcium reabsorption. And if I ask you, which site of nephron where the vitamin D3 is increasing calcium reabsorption? Again, your answer is DCT, DCT, DCT. But what is the mechanism of this vitamin D3 increasing calcium reabsorption? It stimulates the cal binding protein expression. It stimulates the cal binding protein expression. So though more and more cal binding protein will be there in the lumen, and that cal binding protein will reabsorb more and more calcium. Not only cal binding protein, it also stimulates the NCX transporter protein. So more calcium is going to be reabsorbed. Okay, very, very important. Okay, now you may be thinking that, sir, is this TRP V5 and V6, is this transporter is also responsible for magnesium reabsorption? Answer is no. No, sir. Okay. Magnesium reabsorption, even at the level of this DCT, is done by this paracellular pathway. So it is also passive. But Harrison is writing, recently, some carrier protein or transporter protein for this magnesium reabsorption is also discovered. Okay, it's like a channel which is reabsorbing magnesium by transcellular route, and the name of this channel is TRPM6 and 7. TRPM, transient receptor protein, transient receptor. Okay, TRP, transient receptor protein, that is the M6 and M7, right? So that way you have to remember that magnesium reabsorption actively can be possible at the level of DCT, that is by TRPM6 and 7. Okay. Now you know the mechanism of sodium reabsorption and mechanism of other reabsorption at the level of DCT. Okay, and the major transporter which is reabsorbing sodium here is NCC, which is blocked by thiazide diuretics. This NCC, if it is mutated, right, mutation of NCC, the disease is known as Zitelman's syndrome. I hope all of you know. So whenever the person is suffering from Bartter syndrome, which we discussed in the TL segment, or this Zitelman syndrome, the sodium reabsorption is not possible from the lumen or the urine. So these are the salt wasting disease. Okay, salt is wasted in the urine. Not only that, this high amount of salt which is not absorbed at the level of this DCT or at the level of the TL, the Bartter syndrome, that high sodium will be delivered at the level of collecting duct. Obviously, if you don't reabsorb sodium from the TL, what will happen? That sodium will deliver to this collecting duct. More sodium at the level of collecting duct means potassium secretion will be increased at the level of collecting duct. The mechanism I will tell you in the next discussion. But for the time being, remember that Zitelman syndrome is inhibiting sodium reabsorption at the level of DCT because there is mutation of the NCC. So what will happen? Potassium secretion will be more. That's why for Bartter syndrome also, for Zitelman syndrome also, the person will suffer from hypokalemia as well as alkalosis. Okay, the reason will be discussed in the next portion, right? Sodium reabsorption in the collecting duct. So Zitelman syndrome, I hope you got it. Now Zitelman syndrome, hypomagnesemia is also a feature, because you can understand the reason is not known, but probably this DCT segment is that segment where the magnesium reabsorption is also active. So somehow it will be linked to that, and hypomagnesemia is a feature of this Zitelman syndrome. Okay. Now this NCC transporter is negatively regulated by, what I'm saying, there is a regulator of this NCC, sodium chloride channel, tonically inhibited by or negatively regulated by WNK, okay, 4 and WNK1, WNK kinase, okay, WN kinase 4 and 1. Right? So WNK4 and 1 is negatively inhibiting the NCC, negatively regulating the NCC, then this inhibition is tonic. So if this WNK4 and WNK1, okay, is mutated, right, then this NCC will be hyperfunctional, right? So whenever there is a mutation of this protein, then the disease is known as ZOR DON, Gordon's syndrome, right? So the disease is known as Gordon's syndrome. The Gordon syndrome is also known as pseudo, okay, hypoaldosteronism, pseudo hypoaldosteronism type 2. Pseudo-hypoaldosteronism type 2. Getting my point? So whenever there is mutation of this WNK4 and WNK1, the syndrome is known as Gordon syndrome, right? So Gordon syndrome is also known as pseudo-hypoaldosteronism type 2. Why pseudo-hypoaldosteronism? How the aldosterone is related to this WNK, right? So this WNK4 and WNK1 is destroyed by hormone aldosterone. So now you look at the whole mechanism. If aldosterone is there, it is going to inhibit this WNK4 and WNK1. It is going to destroy those. And if it is destroyed, then what will happen? This NCC will be hyperfunctional. Getting my point? This NCC will be hyperfunctional. So that's why this, if this WNK4 and WNK1 is mutated, then also the aldosterone will not be able to work properly. That way, the disease is known as the Gordon syndrome, is also known as pseudo-hypoaldosteronism type 2. So what about pseudo-hypoaldosteronism type 1? I'm coming to that, but before that, you have to discuss the collecting duct mechanism. So now I hope all of you got it, that how the sodium is reabsorbed at the level of DCT. Okay. Now we are going to the next segment, that is sodium reabsorption at the level of collecting duct. Collecting duct, sodium reabsorption. Okay. So again the same thing, the collecting duct contain two main types of epithelium cell. I hope all of you remember that. Principal cell and intercalated cell, right? So the principal cell or P cell, it is a major cell population. 2/3 of the cell population is the principal cell, and only 1/3 of the cell population of the collecting duct is intercalated cell. So whenever we are discussing collecting duct sodium reabsorption, we are going to draw both of this kind of cell. Okay, so let's draw this diagram. This is the P cell, and near to this P cell, I'm drawing this I cell. So this is the I cell, and this red color one is the P cell. Again, this is the luminal side, right? So collecting duct sodium reabsorption from lumen is done by a transporter protein which is absorbing only sodium from lumen to cell, and this transporter protein is known as ENAC, ENAC channel. ENAC, very famous name, you must have heard. Epithelial, E for epithelial sodium channel, that is the ENAC channel. And from the basolateral surface, the same, that is sodium potassium ATPase pump. So whenever sodium is reaching at the level of lumen to cell cytoplasm, that sodium will be thrown to the level of blood by the sodium potassium ATPase pump, and potassium is going to enter here. This potassium will be secreted. Right, into the lumen. So from the lumen, sodium is reabsorbed, okay, and potassium is secreted into the lumen, again by the same kind of channel like that of the TAL, that is ROMK type of channel, renal outer medullary potassium channel, right? Now this nearby cell which I have drawn here already, that is the I cell, intercalated cell. What is the function of this cell? This cell is going to secrete H plus ion, okay, H plus ion. There are two transporters for H plus ion secretion at the level of intercalated cell. One is secreting H plus ion directly into the lumen. This H plus ion is going to cause acidification of urine, and the transporter protein is known as hydrogen ATPase, right? Simple ATPase pump, hydrogen ATPase. Now there is another one also which is secreting H plus ion in the lumen, that is hydrogen potassium ATPase. So this is hydrogen potassium ATPase, means acid secretion by this intercalated cell is a active process. Hydrogen ATPase or hydrogen potassium ATPase, both the primary active transporter. And which variety of intercalated cell? Could you remember? This is I alpha type of intercalated cell. They are secreting acid. Now, why I am discussing acid secretion here in respect to sodium reabsorption? Remember, in the collecting duct, the reabsorption of sodium is linked in such a way that whenever you are taking out one molecule of sodium from lumen to cell, either there will be secretion of one molecule of potassium in the lumen, or there will be secretion of one molecule of H plus ion in the lumen. What I am saying? So again, I am repeating, this is very, very important concept. Reabsorption, okay, reabsorption of one molecule of sodium at the level of collecting duct, it will leads to secretion, of, okay, either one molecule of potassium in the lumen or one molecule of H plus ion in the lumen. Now you are saying either means which one is going to be secreted, potassium or H plus ion? It depends on the blood level. If the blood potassium is high, then potassium will be secreted first from this blood to the cell and from the cell to the lumen, right? But if the H plus ion is high in the blood, like for example, one person is suffering from acidosis, in that cases, H plus ion will be secreted in the urine first. Getting my point? So either there will be secretion of one molecule of potassium or there will be secretion of one molecule of H plus ion. If the blood level of potassium is high, so from the blood, the potassium will be secreted in the urine. If the blood level of H plus ion is high, so H plus ion will be secreted first. Okay. So, you know, if a person is suffering from mild acidosis, okay, if a person is suffering from mild acidosis, so in these cases, whenever collecting duct is reabsorbing sodium, okay, one molecule of sodium, who will be secreted in the urine? H plus ion will be secreted in urine in response to this sodium reabsorption. Getting my point? Because H plus ion is high in the blood in these cases. So whenever one person is suffering from acidosis, for normal sodium reabsorption at the level of collecting duct, you have to secrete H plus ion in the urine, more and more H plus ion. But which molecule is not secreted in the urine in this case? Who is pairing in this case? Potassium will remain in blood, remains inside blood, and that's why potassium level will gradually increase. That will leads to hyperkalemia. That's why we know that acidosis, mild acidosis, means the person will suffer from hyperkalemia and vice versa. If the person is suffering from hyperkalemia, the person will develop mild acidosis. Got it? So this way you have to remember that at the level of collecting duct, sodium reabsorption is coupled with either the secretion of this potassium ion or the secretion of the H plus ion from the nearby cell. Why this is important? Because this collecting duct cell is the site of action of many hormones. What are those? First, okay, aldosterone. So aldosterone hormone, okay, it will directly enter through this plasma membrane because it is steroidal hormone. And this aldosterone hormone, after entering inside the cell, it will act on its receptor. Then hormone along its receptor, the hormone receptor complex, what they are going to do? They are going to activate this INAC channel. They are going to activate this ROMK channel. Not only that, this is also going to activate the sodium potassium ATPase pump. Look at my diagram. So what I am saying that aldosterone hormone, what is the molecular mechanism of action? It is stimulating INAC channel also. It is stimulating the ROMK channel also. So potassium secretion will also increase. It is also stimulating the sodium potassium ATPase pump also. Not only that, due to some non-genomic action, okay, the aldosterone can also stimulate the H plus ATPase pump also. H plus ATPase pump also. So very very important. Aldosterone is mainly acting at the level of P cell, okay, principal cell, but it is also acting at the level of the nearby intercalated cell and secreting H plus ion in the urine. So now you look at, if your aldosterone level is very high in your blood due to certain tumor of aldosterone secreting portion of that, okay, adrenal cortex, okay, so high aldosterone at the level of blood, that is nothing but Cohen's syndrome. So what will happen in case of Cohen's syndrome? The aldosterone level is very high, hyperaldosteronemia, primary hyperaldosteronemia, right? If the aldosterone is high, it is reabsorbing more sodium, increase sodium reabsorption. So what will happen? That will leads to increased water reabsorption also. The patient will suffer from hypertension. Not only that, it is secreting huge amount of potassium at the level of urine via this ROMK channel stimulation. So blood level of potassium will be reduced. So the person will suffer from hypokalemia also, right? Not only that, it is secreting huge amount of H plus ion in the urine. So H plus ion in the blood will be lesser. So the person will also suffer from alkalosis. That's why we know Cohen's syndrome means hypertension along with, okay, your hypokalemia and alkalosis, right? So this way you have to connect that how this collecting duct sodium reabsorption is connected with the potassium secretion or H plus ion secretion, right? Okay. Now this INAX channel is inhibited by another hormone, that is the ANP, atrial natriuretic peptide. Sorry. So this is ANP, atrial natriuretic peptide. It inhibits the INAX channel, right? So atrial natriuretic peptide, it is secreted from atrium myocyte, and from there it is acting at the level of collecting duct of kidney cell. And what it is doing, it is inhibiting the INAX channel. So if you inhibit the INAX channel, sodium reabsorption will not be there. So sodium will be excreted more in the urine, and that's why this is known as natriuretic peptides, right? Similarly, there is an diuretics also, which also inhibit this INAX channel, and that is nothing but amyloride, right? Amyloride diuretics also inhibit this INAX channel. Now you tell me, if you inhibit this INAX channel, sodium reabsorption will be inhibited. So sodium will be excreted in the urine. What do you think? What will happen to the potassium secretion in the urine? It is not going to change. Means whenever you are inhibiting this INAX channel, although you are preventing the sodium reabsorption, parallelly you are also inhibiting the potassium secretion in the urine. That means potassium will spare in your blood, potassium will remain in your blood, and that's why we say this amyloride diuretics is a kind of potassium sparing diuretics. Potassium will be spare in the cell, right, in the blood, sorry, right? Similarly, if you give this aldosterone receptor antagonist, that is spironolactone, the other group of diuretics, okay, the same thing will be done, because this aldosterone is ultimately working at the level of INAX channel. So if you give this aldosterone receptor antagonist, that is the spironolactone, then also you are inhibiting this INAX channel. Inhibition of the INAX channel means sodium reabsorption will be prevented, potassium secretion will also be prevented, and what is going to happen? The potassium sparing diuretics, right? So I told you in the previous discussion that whenever we are discussing here, that if you give this thiazide diuretics, you are preventing sodium reabsorption from this level of DCT. So what will happen? Sodium delivery to the distal part of the nephron will be more. So whenever sodium is more at the level of collecting duct cell, more sodium will be reabsorbed by this INAX channel if the INAX channel is normal, right? More sodium reabsorption means who will be secreted in your urine? Either your potassium will be secreted or your H plus ion will be secreted. That's why I told you, more sodium in the collecting duct means hypokalemia is going to happen. That's why the thiazide diuretics can also produce hypokalemia, because thiazide is preventing sodium reabsorption from the DCT. But sodium will be more in the collecting duct, and collecting duct is normal. So collecting duct will try to absorb more and more sodium. Whenever collecting duct is absorbing more sodium, potassium will be secreted in the urine. So thiazide can also produce hypokalemia by increasing distal sodium content in the nephron, right? So this way you have to remember. Now look about certain mutation. Okay, so the mutation of this inact channel, okay, very very important. Mutation of inact channel. Okay, two types of mutation is possible: gain of functional mutation and loss of functional mutation. So after mutation, there may be gain of function of this inact channel. Typically, this kind of mutation where inact channel is getting mutated and there is increase in function, this is typically happen when the beta subunit or the gamma subunit is mutated. What I'm saying that this inact channel, it has three subunit: alpha, beta, gamma. If the beta subunit or the gamma subunit is mutated, then there will be increase in function of the inact channel, and this disease is known as Liddell's syndrome. Liddell's syndrome. Getting my point? So we have already discussed the Bartter syndrome, that is the disease of the level of TAL. Then Gitelman syndrome, that is the disease at the level of DCT, and now the Liddell syndrome at the level of collecting duct. So in Liddell syndrome, the patient is having hyperfunction of the inact channel. Hyperfunction of the inact channel means more sodium will be reabsorbed. That means this similar kind of feature will be seen. Sodium reabsorption will be more, means the subject, the child will suffer from hypertension, the child will suffer from hypokalemia, the child will suffer from alkalosis. That is the Liddell syndrome. Now, whenever there is loss of function of the inact channel, so aldosterone hormone is not going to function, because aldosterone, the main target of stimulation, is the inact channel. So here, although your aldosterone level is normal, but still the aldosterone will not be able to function. So it's a pseudo hypoaldosteronemia. Okay, which subunit is getting mutated here in this condition? Here alpha, beta, gamma, all subunit will be mutated, and this disease will be known as pseudo, okay, hypoaldosteronism type 1. Did I told you type 2? Yes. The type 2 is nothing but the Gordon syndrome. That is a mutation of the WNK4 and WNK1. That is here. We have already discussed here, I hope. Okay, yes. So this is pseudo hypoaldosteronism type 2. That is nothing but the Gordon syndrome, the mutation of this WNK4 and WNK1. That is the disease of the DCT. But here at the level of collecting duct, okay, if there is mutation of this inact channel, and due to mutation, if there is loss of function, then the disease is known as pseudo hypoaldosteronism type 1. Although there is a second cause of this pseudo hypoaldosteronism type 1, that is aldosterone receptor mutation. Aldosterone receptor mutation. Oh my god. Okay, so the receptor for aldosterone, if it is mutated, then also the similar kind of feature will be there, because the aldosterone will not be able to work, and again that will produce pseudo hypoaldosteronism type 1. So pseudo hypoaldosteronism type 1, two reasons: either the inact channel is mutated or the receptor mutation is there. If the receptor is mutated, generally this is autosomal dominant variety of disease, and this inact channel mutation, this is a kind of autosomal recessive variety of disease. So AR variety of disease is the inact channel mutation, and AD variety of disease is aldosterone receptor mutation disease, right? So this is all about the sodium reabsorption at the level of collecting duct, which is occurring through which cell? P cell or the principal cells. Now, could you recall another function of this P cell or principal cell at the level of collecting duct? Answer is yes. The same P cell, the principal cell, is also responsible for water reabsorption. So sodium reabsorption, potassium secretion, and now the third one is coming. This is water reabsorption from lumen to the cell cytoplasm by a aquaporin channel, and this aquaporin, okay, is aquaporin type 2. For absorption of water from this basolateral aspect, there is another subvariety of aquaporin, not only one, there are two subvariety of aquaporin which absorb water from cell cytoplasm to the blood. Here the aquaporin which is present is aquaporin type 3 and aquaporin type 4. Now remember, aquaporin type 3 and aquaporin type 4, both of them are constitutively expressed on the basolateral membrane. They are always present on the basolateral membrane, right? But this aquaporin type 2, they generally remain inside the vesicles. Suppose this is a vesicles inside this P cell, okay? And inside this vesicle, the aquaporin type 2 channel is there, okay? It is not on the membrane. So someone has to bring these vesicles from this cytoplasm up to the level of this membrane, and then only the water reabsorption is possible from lumen to the cell. So aquaporin type 2 channel, generally it is normally present inside the cell cytoplasm, inside a vesicle. Someone has to bring this vesicle from cytoplasm to cell membrane, and then you input the channel or membrane, then water reabsorption will happen. Who is going to do this? One hormone. Which hormone? The famous hormone is ADH. So ADH has its receptor on basolateral aspect of this cell. So the basolateral aspect of this cell contain a receptor which is the V2 receptor, vasopressin receptor type 2. ADH, if it is high in the blood, it will stimulate this V2 receptor. That V2 receptor will produce a second messenger, that is the CMP. That CMP is going to stimulate these vesicles, and the vesicle will move towards the cell membrane, and the aquaporin 2 will be put into the membrane. So if I ask you, ADH is stimulating which aquaporin? That is aquaporin type 2. Can ADH stimulate aquaporin 3 and 4? Answer is no, no, no. So I'm writing here very, very important mechanism. ADH is stimulating V2 receptor which is present on which membrane? Basolateral membrane. Because of this stimulation, there will be increase in CAMP. Increase CAMP means it will stimulate the aquaporin channel type 2. This will leads to increase water absorption from collecting duct. So this is all about sodium reabsorption from different part of the nephron. And not only sodium reabsorption, there are many reabsorption which are coupled to sodium reabsorption, which we have discussed here.